The energetics topic is all about energy, and you need to remember the principle that energy can neither be created nor destroyed, but you can convert it from one form to another. And in any chemical reaction, you're going to have some form of energy change. If we think about the heat content, then we're actually talking about enthalpy. So if we're talking about an energy change in terms of heat energy transfer, we term that as an enthalpy change. All you can measure is an enthalpy change. You can't actually measure the enthalpy of a substance. And we represent enthalpy change as this symbol here, little triangle, which is the Greek letter delta. So we say enthalpy change is delta H, where the delta means change and the H means enthalpy. If you want to calculate the enthalpy change, then you take the enthalpy of your products and you subtract the enthalpy of your reactants to get the difference between the two. We can represent enthalpy changes using an enthalpy change profile or an enthalpy diagram. And that shows, it says here the reaction coordinate, but that just means kind of as the reaction progresses, so over time. And then on the other axis you have enthalpy. If you have an exothermic reaction, that's one where heat energy is given out. So that means that your reactants have more energy than your products. Your reactants have lost heat energy, and that has been given out to the surroundings, and therefore your products are of a lower energy. So we say we have a negative enthalpy change because heat energy is given out, it's given away. Don't forget that you need to draw in this arrow here, which represents your activation energy. So as we go from the start of the reaction to the end of the reaction, the reactants to the products, actually we've got to overcome this activation energy, the minimum energy required for a reaction to happen. Looking now at our endothermic reaction, you can see that actually here the reactants are of a lower enthalpy than the products. That makes sense if you think about it, because an endothermic reaction is one where energy or enthalpy is taken in to the reaction mixture. And so if you take in enthalpy, then that means you're going to get a positive enthalpy change. You're going to get an enthalpy increase in this reaction where you have absorbed heat energy. So that gives you a positive delta H or a positive enthalpy change. Some common examples of exothermic ones that have a negative delta H, a negative enthalpy change, are combustion of fuels. So if you burn a fuel, you're going to get heat energy given out. And respiration, if you carry out the respiration reaction, then you're going to give energy out, heat energy out. The opposite of respiration is photosynthesis. So if you think of it as a kind of not a reversible reaction, but the opposite of respiration is going to be endothermic. Thermal decomposition, so where you're putting in heat to break down a chemical, so for example calcium carbonate breaking down into calcium oxide and carbon dioxide, you're putting in heat to make that happen, so that is an endothermic reaction. We sometimes describe an enthalpy change as a standard enthalpy change. And that's because your enthalpy values, so the energy in terms of the heat transfer, vary depending on your conditions. So if we have a standard enthalpy change, that's where the substance, the chemical that we're looking at, will be in its standard state. It'll either be a gas, a liquid, or a solid at 100 kilopascals of pressure and 298 Kelvin, which is 25 degrees Celsius. So that tells us what state it'll be in, solid, liquid or gas. And you also have to remember that any solutions, anything aqueous, is going to be of a standard concentration of 1 mole per decimeter cubed. If we have standard conditions and we have a standard enthalpy change, then we just add this little symbol here to show that. So that shows that we have standard conditions. We have that 100 kilopascals of pressure and that 298 Kelvin. If we're looking at an enthalpy change of reaction, you do need to know the definitions for all of these different enthalpy changes. Enthalpy change of reaction is the enthalpy change that happens for a given chemical reaction. Enthalpy change of combustion, which is shown with a little c here, is the enthalpy change when 1 mole of any substance undergoes complete combustion, so where it reacts completely with oxygen to make carbon dioxide and water. If you have standard enthalpy change of combustion though, just make sure that you remember that that is the enthalpy change when 1 mole of a substance undergoes complete combustion, reacts completely with oxygen to make carbon dioxide and water, under standard conditions where all reactants and products are in their standard state, so the state, solid, liquid or gas, that they will be in at those given pressures and temperatures. If you get asked for a definition in the exam and it has this little symbol that shows it's under standard conditions, you have to include the phrase standard conditions in your definition, and you have to include the phrase that all reactants and products are in their standard states. Enthalpy change of combustion is always exothermic, it always gives out heat energy. And you've got a couple of examples here. We said it's where it reacts with oxygen, and it's where you just have 1 mole, so where you just have 1 molecule reacting with oxygen. Another enthalpy change that you need to know the definition for, you need to understand what it means, is the enthalpy change of formation. This one's represented with a little f next to it instead of the C for combustion. And the definition is that this is the enthalpy change when 1 mole of a compound is formed from its elements. So the separate elements join together to make 1 mole of a compound. Again, if it says standard enthalpy change of formation, same definition, the enthalpy change when 1 mole of a substance is formed from its elements, but this time don't forget to put in its standard state, from the elements in their standard states. And I'd also actually add in that that is under standard conditions. These are usually exothermic reactions. It's where you have your separate elements, for example here carbon, oxygen and hydrogen, reacting together to form just 1 mole, just 1 molecule of the product. If you have an element, then the enthalpy change of formation for that is 0, because if you're forming an element from its elements, then you're already there. You're not actually making any kind of change. You're not needing to say that there's any kind of enthalpy change. It says here about carbon usually being taken as the graphite allotrope. Just remember that carbon can be found as your diamond as well, so that's a different allotrope, a different version of carbon, and we tend to say as standard carbon is in the graphite form. Your final enthalpy change that you're supposed to know the definition for is enthalpy change of neutralization, which is just represented like NEUT next to your delta H next to your enthalpy change. And the definition here is enthalpy change when, again, 1 mole, that's common, it runs through all of our definitions. Enthalpy change when 1 mole of water is formed from its ions in a dilute solution. So that's where you're getting your H plus from your acid reacting with your OH minus, possibly from your alkali, to form 1 mole, 1 molecule of H2O. And these tend to be exothermic reactions, so they will have a negative enthalpy change. This next definition isn't actually an enthalpy change, it's your bond dissociation enthalpy. So that is the enthalpy required to dissociate, to break up a bond. So the energy required to break 1 mole of gaseous bonds to form gaseous atoms. This is always going to be endothermic, so you've got to put in energy in order to break a chemical bond. So an example is going from the Cl2 where it's bonded together to the separate Cl atoms. The strength of that bond depends on its environment, so that's why we give a mean value, an average value, because a carbon bonded to a hydrogen would be slightly different in different environments. If you make bonds, then that is exothermic, that's the opposite of breaking a bond. And we have something called the enthalpy of atomization, which is where you form just 1 atom. And if you have a diatomic gas, then you're obviously forming 2 atoms. So the bond enthalpy is twice the enthalpy change of atomization. If you have a smaller bond enthalpy, that actually just means you've got a weaker bond, so it'd be easier to break that bond. If we look at a few examples here, you can see here, for example, your carbon-carbon double bond is a higher enthalpy than your carbon-carbon single bond. So your carbon-carbon double bond is actually stronger, and then your triple bond is stronger again. You have your hydrogen-hydrogen bond, about 436, and then other common ones you might be familiar with: CO, C double bond O, CH, all things from your organic chemistry perhaps. You do not need to know these off by heart. These values will be provided for you in the exam. If we're thinking about the enthalpy change of reaction, so going from A to B, the enthalpy change of reaction can actually be represented in a slightly different way. So we can actually say that the enthalpy change is independent of the path taken, and this is known as Hess's law. What it means is you could go direct from A to B, and that would be your enthalpy change of reaction, or you might actually go via some intermediate or some other product, and that would give you several different enthalpy changes that would all add together to give you the same value as your enthalpy change of reaction. So whatever your enthalpy change of reaction is equal to, the alternate path that this reaction can follow would just be adding up those individual enthalpy changes so that they were equal to your enthalpy change of reaction. That allows us to calculate enthalpy changes from other data. So even if we weren't sure what the enthalpy change of reaction going from A to B was, if we knew these three other values, we could work it out. Or alternatively, if we knew what the enthalpy change of reaction was and we knew two of the other values here, we could use a little bit of algebra to work out the third one. So this is really used for calculating enthalpy change of reaction from bond enthalpies and enthalpy change of reaction from your enthalpy changes of combustion with a C and your enthalpy changes of formation with an F. Taking that first example where we're going to calculate an enthalpy change of reaction, so going from reactants to products for a certain chemical reaction using average bond enthalpies, then what you've got to do is you've got to kind of think of it as all the bonds breaking and then the individual atoms joining up again to form the products. And the overall energy change, the overall enthalpy change, will depend on the difference between the energy needed to break those bonds of your reactants and the energy needed to be released when you make the bonds in your products. If the enthalpy, or the energy rather, used to break the bonds is much less than the energy released making bonds, then what you're going to have is you're going to find that there's more energy released, more energy given out, a negative enthalpy change, and that is an exothermic reaction overall. If you have it where the energy used to break the bonds is greater than the energy released making the bonds, then actually you're going to use up more energy. You're going to need to take in more energy than is released. And so if you take in more energy, that is going to be an endothermic reaction. If you look at an example like this one here, we've been given the reactants and the products, and as we said, you've got to imagine all of these bonds breaking. So the CH, 4 of those breaking, the C double bond C breaking, and the H bonds breaking in the middle there. And then you've got to imagine making all those bonds and forming your CH bonds and your CC single bond there. If you think about the total energy required to break the bonds of the reactants, then that will be 1 carbon-carbon double bond, 4 carbon-hydrogen single bonds, and 1 hydrogen-hydrogen bond. That gives you a total energy required to break the bonds of all the reactants of 2699 kilojoules per mole. Your enthalpy changes are always measured in kilojoules per mole. Then thinking about all the bonds that need to be broken to get your product into the individual atoms, you need to break 1 carbon-carbon single bond and 6 carbon-hydrogen bonds, and that gives us a total of 2824 kilojoules per mole. If you apply Hess's law, we're saying that you can either go straight from reactants to products, or I can go around from reactants down to the individual atoms to the product. So those are my two paths, and those two routes are equal. So your delta H1, your enthalpy change of reaction, is equal to your delta H2, and then actually we're going in the opposite direction to delta H3. So we're actually talking about making the bonds rather than breaking the bonds. So we would actually say that your delta H1, enthalpy change of reaction, is equal to the breaking of the bonds minus the breaking of the bonds, because actually what we're doing is making the bonds. So just be careful, if you go against an arrow as you're drawing that path to go from reactants to products, then you actually have to put it as a negative instead. That means when we take our bonds broken, 2699, and then take away these bonds here, 2824, we get a sum total of minus 125 kilojoules per mole, it should say on the end there, because it should always be in kilojoules per mole, and that is your enthalpy change of reaction. You can do something similar with your enthalpy change of formation. So if you think about going from your reactants to your products, that's your enthalpy change of reaction. But we can also think about forming your reactants from their elements and forming your products from their elements. And so actually you should need the same amount of every substance if you form the reactants as if you were forming the products. So whatever elements, whatever atoms you need to use to make the reactants, if it's a balanced equation, you should require the same atoms to make your products as well. So that means that we can actually say that the enthalpy change of reaction is equal to the enthalpy change of formation of the products, take away the enthalpy change of your reactants in terms of formation. If you think again about your different paths, yes, we can go straight from A to B, but alternatively we could go from A to B via the elements here. And that's why we've got the enthalpy change of our products as the positive one. And we've actually gone against the arrow for the enthalpy change of formation of our reactants, which is why we've got a negative in front of our enthalpy change of formation of the reactants. Again, a similar principle applies if we're talking about using enthalpy changes of combustion. If you burn all of the products, you should get the same amount of CO2 and H2O, the oxidation products, as if you burn all of the reactants. So the enthalpy change of combustion of the reactants and the enthalpy change of combustion of the products can be used to work out the enthalpy change of reaction overall. So here, if we're using combustion, it's the opposite to your enthalpy change of formation being used to work out the enthalpy change of reaction. Actually here what we've got is, if we want to know going from A to B the enthalpy change of reaction, we have to go A round to B. And what you've got there then is you've got your enthalpy change of combustion of your reactants here, and then you're going against the arrow for your enthalpy change of combustion of your products. So going against that arrow there means we have to put the negative sign in front, and that's why it's minus the enthalpy change of combustion of your products. These signs here just mean that we're doing the sum of the enthalpy change of combustion of the reactants and the sum of the enthalpy change of combustion of the products. So you do need to take into account how many moles of each thing you've got in your balanced equation. So for example here, if I'm trying to calculate enthalpy change of reaction, I need to take the sum of the enthalpy changes of combustion for the reactants, carbon and 2 of hydrogen. That's why we've got 2 there. That's what I meant when I said take the sum of. It's your carbon and your hydrogen, and it's the fact you've got 1 carbon and 2 hydrogens. And then you're going to subtract your enthalpy change of combustion of your products. So subtract your enthalpy change of combustion for your products here to give you the total enthalpy change of reaction. Again, you don't need to know these values. They'll be given to you in the question. So your Hess cycles are a theoretical way of measuring your enthalpy changes, or not perhaps measuring them, but working them out. However, you can do a practical, an experiment called a calorimetry experiment that helps you to determine, to work out enthalpy changes. Usually that involves heating up a known amount of water, so a certain number of millilitres or centimetres cubed, as we'd probably refer to it as. If you're heating up your water, then that's obviously an exothermic reaction that's doing the heating. If you're cooling down your water, which is less common, then what you're doing is an endothermic reaction. The calculation that you need to do is actually working out the energy required to change the temperature of a particular substance. In this case, the substance is water, and Q is your heat energy that's required to change the temperature of a substance. M is your mass, and that's actually the mass of the substance that you're changing the temperature of. That's the mass of the water. C is known as your specific heat capacity, and for water that's always 4.18. And delta T, just like delta H is your change in enthalpy, delta T is your change in temperature. So if you started to heat up some water of a certain mass, then you could take the mass that you know, because you could weigh it, of your water, take the specific heat capacity, and then see what happens in terms of the change in temperature to work out the heat energy that has been transferred to that water. You can do this graphically, so you can do it where you actually take the temperature before you've mixed the reactants. So you see what the temperature was at the beginning, you mix your reactants, the reaction happens, you get your increase in temperature, and then you have to kind of extrapolate, you have to extend these lines that you've been drawing on your graph so that you can try and work out what the total temperature change was. That can then allow you to substitute that into your heat energy calculation here. In the exam though, they're more likely just to give you a temperature change, so here 22 degrees Celsius to 47 degrees Celsius. What you need to do is you need to work out the heat absorbed by the water. Remember, it is the mass of the water. They'll sometimes throw in the mass of the chemical. You'll need that later on to work it out per mole, but be really careful here, the masses of your water, and you want that in kilograms. We said your specific heat capacity is always 4.18, and if it's gone from 22 to 47, then that's 25 degrees Celsius. If you do that multiplication, you get the heat absorbed by the water as 10.45 kilojoules. I said that they'd given you the mass of the chemical. If you know the mass of the chemical, you can work out how many moles of the chemical you have using your amount of substance calculation of moles equals mass divided by formula mass. So the formula mass of hexane you could work out from the periodic table is 86. So in this experiment, to get 10.45 kilojoules of heat absorbed by the water, we used 0.00209 moles of hexane. So if I actually wanted this per mole, I would need to divide by the number of moles that I've actually done it for. So you take the heat energy and divide by the number of moles to get it in kilojoules per mole. Your enthalpy change, remember though, actually is going to be the opposite sign to what your heat absorbed is. If you have a temperature increase, that must be an exothermic reaction, so that must be a negative enthalpy change, and vice versa. If you had a negative temperature difference, if the temperature went down, that would be an endothermic, so that should give you a positive answer at the end. So don't forget this little bit here where you just need to think about the sign of your final answer. Was it an endothermic reaction, temperature decreasing, or was it as an exothermic reaction, temperature increasing? And just put the appropriate plus or minus sign for your enthalpy change.